All right. So today for our data structures lesson, we are going to do a bit of a review of bubble sort and insertion sort. We'll kind of refresh ourselves on big O and what it is. And then we are going to really dive into merge sort and divide and conquer algorithms, of which merge sort is one of the big examples. So why does this matter and why are we doing it? These are sort of like the bread and butter algorithms that everyone who takes a computer science class learns to start learning about runtime complexity. It accomplishes a couple things. It might come up in a technical interview. It's not as often as you think, but it does happen. More importantly, I think it gives you the knowledge that you need to keep building. And one of the analogies that I sort of like is that learning computer science as a programmer is like a family physician learning about DNA, right? If I'm a family doctor, I'm probably not doing like DNA recombination or God knows what all the time, but it's really important foundational knowledge and to sort of speak the language of my professional peers, I need to know it. It also sets me up to go deeper into things when I need to. It will also help you with problem solving as you see different ways of doing things. And then finally, with merge sort, and specifically with divide and conquer algorithms, this divide and conquer approach we actually see all over the place. And it is super valuable. So let's go ahead. Let's write an implementation. Let me talk through what bubble sort does, and then we'll write an implementation of it. And in fact, yeah, let's write some code and I have a nice visualization for us. So bubble sort, right? Bubble sort goes through a list over and over until everything is sorted and out of place items bubble to the correct spot. It uses a nested loop. Because of this, and we are not going to really need a Python interpreter uh, for installing dependencies, so that's okay. So because of this, it's big O, its worst case runtime complexity is big O of n squared. And let's just kind of get our brains back in algorithm zone as we write this this function out. So bubble sort is going to take an array, and I'm going to need the length of that array. And I need to make a nested loop because I want to compare each item to every other item. And this part is important as I build out this nested loop, right? And if I was to draw a little diagram here, and let's put some values in here. And why don't we have this hold 4, and then it can hold 3, and it can hold 2, and it can hold 1. And as I'm building out my loop, I'm going to need some pointers. right? And we're gonna have our first pointer I and our second pointer J. And we'll kind of put I up close and we'll make J a bit longer. And remember, what I want to do is I want to compare my first pointer I to this guy, this guy, this guy, right? And then when we're done looking at the first item in the list, we need to move to the next and compare it to this guy, and so on. And so that's why when I'm building my nested for loop, the outer loop loops over the whole thing, but the inner loop is only going as far as I minus one. And I want to now do some comparisons. And if J is greater than J plus one, then we need to do a swap. And if we add a print statement here, we might say comparing these two to each other. And then we might say they're out of order and we're going to swap. And then we might say, once we've finished that if statement, we might print out the array looks like. And if I then ran this guy, let's do bubble sort for these same numbers. And well, it looks like actually I've made an error here. So we're correctly identifying when something's out of order, but it looks like in my swapping, I screwed something up, right? And I'm overwriting a value. Um, this started out 4-3, but it looks like the numbers are getting replaced. So, oh, Tom, yes, sir.
For the reassignment, wouldn't we either A, need a holder variable, or couldn't we do ARR at J, comma, ARR J plus one equals, and then flip them?
I think that's exactly what I did wrong, because that's in fact what we have in the example code. And I kind of try to avoid that, but I think you're right. If I do it this way, I need a holder. I think I would need, uh, let's just call this original J. And We'll call this in fact original J value. And we set J to J plus one. And then I think this is probably where I had my overwriting happen. Does this look right? And now we need to replace this with the temporary value. Let's see if that does the trick. Yep. Thank you so much, man. That was a great call. Um, yeah, I try to avoid you can write this another way where you combine these on the same line and it does the swapping. I think it's a little risky because it's easy to introduce programmer error. This way we have to add the extra sort of temporary placeholder, but it makes the code a little easier to modify and reason about. Um, so we can now see our swapping happen. And while this is cool, it'd be nice if we could get an even cooler visualization. And as it so happens, there's a great site, PyAlgoviz, and it does require you to sign in with your with a Google account. But what it gets you, and what we're going to see here is while their implementation isn't quite the same as ours, it's a nice bubble sort. You can in fact see the visualization code here that uses a Python visualization library, and we can slow this down to like molasses speed. And what's happening here is they're generating basically, I think, like 30 random numbers. And now we can run bubble sort and we can watch it run. And we can watch, and now it's the algorithm has restarted, right? And we can see the bubbling happen. And frankly, molasses is maybe a little too slow. And we can see why the algorithm is named bubble sort, right? As that like biggest item is just bubbling forward. And I do always get a little confused when I'm visualizing this. I forget that the I and J kind of start at opposite ends. And so I probably got that confused in my TL draw. But here we can get a really nice visualization of the algorithm. And also hopefully this helps illustrate why its worst case runtime complexity is big O of n squared, right? Because in the worst case, I basically need to loop through this entire algorithm, however many elements big it is, like that many times. If I've got 10 items, I got to go through my list of 10 items 10 times to get everything in order. And we can kind of speed it up and speed it up a bit more. And we can see the sorting in action, right? And we can see the bubbling. So I really like this PyAlgoviz site. Um, and this is just sort of getting our brains warmed up as we're looking at code to kind of get a visualization of algorithmic complexity. So I just want to check in to see what questions folks have. What might be good to go over here or review a bit with regards to bubble sort or this idea of the in the worst case scenario, it's going to take n squared times to sort this thing where n is the length of our list. So what questions do folks have and what's on people's minds? Okay, so I do have one question here, which is we've talked about bubble sorts worst case, but is there a way to make bubble sort perform better some of the time? How can bubble sort know when it's done? For instance, let's hop back to our code here and let's modify this a bit. So maybe it looks like maybe instead of 4, 3, 2, 1, we had something like 5, 4, 1, 2, 3. And if I run this and we look at our print statements, note how right? We're sorted, we're moving that five. Over here, we've got 4, 1, 2, 5, 3. Here we have 4, 1, 2, 3, 5. Finally, we get 1, 2, 3, 4, 5. But we still have these two extra operations where like our list is already sorted, but bubble sort doesn't know it. And it continues comparing and looping through the loop, right? And let's see if I can add this here. If we comment this out and we say data equals 4, 5, 1. Let's add a couple extra. So let's make it like uh 4, 5, 1, 2, 3, 4. Let's do 5, 6, and we'll make over here, we'll make these 7, 8. And let's see if this will run nice and we can kind of see bubble sort doing some extra work and talk a little bit about what we can do about it, if anything. Let's have this run at snail speed and let's go ahead and save and run our code. So we need to have this run slower. So it needs to, there we go. So this is running really slow. Let's speed it up just a touch. So we can see that it's doing these comparisons and it's sorted, but it doesn't know it's sorted and it keeps comparing, right? Now, we're not going to be able to change the worst case performance. Big O is going to stay n squared no matter what. But right now, it's actually kind of doing extra work for like a best case and maybe even an average case. So how could bubble sort know when it's done? Tom, yes, sir.
Could we find the min and max values and tell it it's done when the min is in zero, max is in the end?
Say that one more time.
Find the min and max values and then tell it it's done when the max value is at the end of the list and the min value is at the beginning.
Sort of finding the min and max values in the list in this case is a little bit like cheating because that's sort of doing the sorting for us. On a practical level, though, you're correct. Rick, yes, sir.
I was I was gonna say something similar, but and you could do like a in the loop. You could do an if statement. Well, there is an if statement, but like you could say if uh yeah, something like that. Like if index 0 is less than index the len index the final index at the end. Um, something like that maybe, but like you said, it is kind of like cheating. So I don't know if that would be something we could do with like an if statement. If something is less than the final, then you're
Right.
good. But
Yeah. So you're on the right track here. What, because you guys are on the right track, we need to kind of know, is there a way that I can tell that bubble sort is done? Right? It's I think going to be tricky looking at min and max, but if we look at the behavior of this algorithm, what we see is when everything is sorted, it stops swapping, right? And I saw a couple of hands up, and I apologize, just in the interest of time, I want to dive on to make sure we can cover some other things. So swapping is what I'm talking about when it finds that two items in our list are out of place. And let's go back in time here with our visualizer, right? And so we see that that guy in red there is not in the right spot. And once bubble sort sees that, it swaps them. right? And if bubble sort loops all the way through once without swapping, then we know everything is in order. So if I can keep track of if I've swapped or not, then we can finish up a bit early. And in fact, let's add here the numbers that we had there. And let's add our swap variable and see what this looks like. So what I want to do is every time I start a new loop, right? I set swaps to false. I haven't swapped anything yet. If at some point in the loop I hit my if statement and I do update these values, we set swapped to true. And that's how I can know if I'm done or not. Right. And I'm making sure I have my levels right here. Here we go. I can say if we have gone a whole loop without swapping, the list is sorted. Right? Because to go back to this illustration, I'm kind of gonna move back in time here a bit. Right? When it's out of order, we're swapping positions. But if I go all the way through one loop comparing all the items and nothing is swapped, then we know that everything is sorted. So let's put this print statement there and say if not swapped, we'll just print list already sorted and we'll exit our loop. And now if I run this code, let's see, did I put something in the wrong spot if I look at these print statements? Because we have, I think I did put something in the wrong spot because we have all these comparisons. Sam, yes, sir.
Does the swaps need to be in the outer loop, not the inner loop?
Say that again.
I could just be looking at your code wrong, but doesn't the swaps need to be in the outer for loop, not the inner for loop?
Yeah, you're totally correct. That's just my brain looking at Zoom too long. Because every time I start a new loop, I want swap to be false. Yeah, good call. Thank you. All right, on day one of class, that would have been a lot tougher. So we're close. This we set swap false, but I think this if statement
Is it
it looks like
because Python reads from basically top to bottom? You need to put the if statement. Well, swapped. No, I think false swap needed to go somewhere else because like every time the loop starts, it. Well, no. Maybe
yeah,
the if
let's
statement not in the for loop, maybe.
yeah, let's see here. So our outer loop, then when we're comparing one item to everything else, we set swapped to false. Then if I make it all the way through this inner loop, I want to check if swapped is false. We print list already sorted. Uh, I think the issue here is actually just this particular example may be a little too good because sort the whole thing in our first loop through. That might be the problem. If I add like 1.3 and like 2.6, let's see what happens. So it takes a lot more iterations now, right? Because a lot more things are out of order. Um, I apologize, guys. I actually may have to come back to this one because it looks like we still have all these comparisons where we're not swapping. Um, I think this is actually working okay. I think the issue is I have my print statement inside the inner for loop. If we move it outside, let's watch what happens. I think that's actually the issue here because I think what's happening is we loop through everything once, but my print statement was inside that, so we were seeing that all the time. And my swap only works by checking when we're done with the end of a full loop.
Wow.
And now I think this is what I was expecting to see, where we see list is already sorted and we stop. Um, and if we added a counter and we tried it without swapped, I think we'd end up doing extra iterations. And I think indeed that was my issue was the placing of this print statement. Which is a common error where sometimes it's not the code, it's how we're like analyzing the code. Rick, yes, sir.
Yes, this may make it more efficient, but um, the time complexity is still the same because I mean, you still have to take into account like worst case scenario. So it would still be O of n squared.
Yeah, that's correct. The worst case scenario is unchanged. It's O of n squared. Um, what this does mean though is if we have lists that are more sorted or better sorted, our average case or our average case performance goes up a bit. Um, really my goal here though was just for us to start kind of digging in to algorithms a bit, right? Because you're absolutely right that the worst case performance is unchanged, but like we now really understand like how does this work? How does this algorithm know when it's done? What does it need to keep track of to know if it's done? And how the performance of my algorithm is going to vary depending on what kind of data goes into it, right? However, you're absolutely correct. The worst case big O performance is totally unchanged here. All right. Um, why don't we take 5 and then we'll take a look at insertion sort and then we'll move on to sort of like the heart of today's lesson, which is merge sort. Just to recap, we've implemented bubble sort. We've kind of gone through a nice visualization of it. We've debugged a couple of issues along the way. We've reviewed what a big O of n squared or quadratic time complexity algorithm looks like. And we've seen how I can improve the performance of this algorithm for some cases, for some data, but its worst case performance is unchanged. Um, most of the time, you will only care about the big O worst case performance, but it is good to know how like changing the kind of data or the shape of data, how different algorithms can perform differently, and also being able to kind of like tweak and play around with algorithms like this, because then as things start to get more complex, it becomes easier for us to modify and work with them. All right, guys, thank you very much. Let's take a short break and we'll pick it back up in 5. All right, let's take a look at another big O of n squared algorithm called insertion sort. And it is also big O of n squared. it is similar to bubble sort, but not the same. It performs better than bubble sort on partially sorted lists. And while this doesn't change its worst case runtime complexity, again, just in terms of learning how to think about and analyze algorithms, this is useful to see. And insertion sort forms a partially sorted array as it sorts a list. And let's see this in action. So like bubble sort, we're going to end up with two nested loops. And I'm going to use a placeholder variable item to keep track of our comparisons. And what I now want to do is I want to compare item to its left neighbor, which we'll call J. And if J is bigger, we shift J right. Otherwise, we decrement J and keep comparing an item to it and shifting until J is smaller than our item. And let me write this code and then we'll kind of walk through it. So J is going to equal I minus 1. Right, so over here, we can kind of see I built up an example list and I starts at index 1 and J is actually at index 0. And we're actually going to use my least favorite kind of loop, the while loop here. And we're going to say, well, J is greater than or equal to 0 and item is less than the value of whatever is at J. We're going to do a swap and we're going to decrement J. Right, so if 2, let's see if I have this right here. Yep. If this is less than this guy, then we need to swap and we need to decrement J. But if item is bigger than array of J, we're going to insert item to the left of J. And then everything in the list up to index J plus 1 is guaranteed to be sorted. And let me write this line of code. And return our sorted array. Now, the challenge here is always in not writing the code, but then reasoning about it once it's done. And let's go ahead and run insertion sort and let's run it for our data that we see in TL draw 3, 2, 1, 4, 5, 9, 6, 7. And what did we forget to do here?
you're calling the function inside the function.
Oh, thank you so much. There we go. I was wondering why that was grayed out. Best kind of error to have. So we see this sorted, right? Not very exciting. Let's put a print statement at the top of our while loop. Let's see the array printed out as we go. And note how this becomes sorted, right? And we have this sorted sublist that gets built up here. And I'm not gonna lie, I always find moving through this manually a little tricky, but this is also the best way to really get to know an algorithm. So we're looping through I from beginning to end. Well, with I starting here at index 1, and J is starting at index 0. And we're saying, well, J is greater than 0. And item, well, what is item? Item is over here at index 1. So item is going to be, and let's make this really big. Item is 2, right? So J is greater than 0. And 2 is indeed less than array of J, which is 3. So let's in fact put something here as well to help us keep track of things. So I need to swap. I need to say that array of J plus 1 now equals J. So over here, we need to set, let's see if I can get this right. We put 3 over there. And our item value is still 2. And we say array of J plus 1 equals item. And I feel like I've got something wrong in my logic here because they're definitely swapping. Oh, and in fact, it works. This is where this algorithm, in fact, I'd say is genuinely confusing because only in this situation at the very beginning, where we're actually decrementing J when it starts off at index 0, it actually goes to index -1 for a little bit. And so then -1 plus 1 takes us back to index 0, and then 2 gets put over there. And that always confuses the heck out of me. But this is why the devil is in the details with this stuff. And so now we have completed that swap and we move on to the next item in our list. And so now I moves forward, right, to index value 2. And we set J to I minus 1. And we do the same thing where item is 1 and array of J is 3. And now we're going to compare. Well, J is greater than equal to 0. Item is indeed less than array of J. So I need to swap. J plus 1 becomes J. So 3 gets moved up here. And actually, item is not 2, item is 1. Right? Item 1 has been moved out, and 1 is our item. J gets decremented. So it goes back down. And now we're comparing this item 1 over here. And well, 1 is indeed less than 2, right? So rev J is now 2. And so we swap, right? And 2 gets bumped up. And this funky behavior happens again where J goes kind of into like the final gear of -1. And then with this J plus 1 gets kicked back up. And then our item value is dropped in there. And we have 1. And so what's happening here, it's sort of like a bubbling in reverse, right? And let's go up here to 9, where something's out of order, and we can really watch this happen and walk through this a bit quicker. Um, well, we see that these guys are out of order, and so, oh, excuse me, it's not going to be 9, it's going to be 6. We see that these guys are out of order, right? 9 is bumped up there. And we're just comparing item to each of these until we find where it belongs. And then, in fact, we would find it belongs here. And then things would keep bubbling backwards. And let's actually pull this one up in PyAlgoviz because this one is good to see as well. And so there's a visual breakdown of it here. Insertion sort actually performs better for almost sorted lists. There's a term for this called a k-sorted array, which if you want to kind of go into the weeds, you can check out. And let's pull up our, here we go. We can see our PyAlgoviz insertion sort. And we'll let it run really slow. And that might be a little too slow. And you guys see how J is moving backwards and the list is sorting itself as we go. Right, so it's kind of like the opposite of bubbling. And you could also see how if the list was already partially sorted, that this algorithm might perform better than bubble sort, and in fact does. Right, so I got a little lost in the sauce at the end of doing it manually, but I think PyAlgoviz is a really useful tool for stepping it through. And this is also part of the value of kind of learning this stuff. It's sort of like, I think of it as like strength training for programming, right? It really forces you to flex certain mental muscles. So I just want to pause and check in here and see what questions folks have or what people might be curious about. Tommy, sir.
If we're temporarily going to -1 for an index value, why isn't it throwing a index out of range error?
Yeah, it's a great question. Because right here on line 28, um, so right here is when we decrement J, and this is when it might temporarily take J into -1. But then on this next line, we do J plus 1, and that's going to bump it back to 0. So it's sort of like a guardrail, and also like a very sort of clever, I think, design. And also like genuinely confusing. Which is why, again, it's useful to walk through this stuff. But because of the way that this is set up, we only go to -1 right here. And then right here, we would bump J back up to 0. And then we start a new upper level loop again with a new value for I and a new value for J. Does that help break it down?
Yeah.
Yeah. I think that's the tricky bit of insertion sort. And kind of it feels like it's like working by breaking the rules, but it turns out to work just fine, right? Rick, yes, sir.
Yeah, really, just a comment to just echo off of what you were saying about different muscles. Never really thought of that until I got to this class. And yes, some of these algorithms, like rarely I might use one, but usually it's a very simple algorithm in like, coding a project. But yeah, I definitely agree that it seems to be like different muscles because when you're doing algorithms, it just seems like you're doing algorithms intentionally, and when you're doing a project, you're not really thinking about algorithms, and every once in a while you might use one, but it's not as a like front in your face kind of thing that you think about when you're programming.
Yeah, exactly. It's like you might see little bits of these things pop up. Like you might encounter a situation where you're working with a list where you have to like deal with a pointer going temporarily to like a -1 value, or you might have some sort of like bubbling behavior or inserting behavior. It's I kind of think of it as like the DNA of programming. You don't like see it show up there exactly, but it's kind of there's a little bit of it everywhere. On that note, let's take five, and then when we come back, we will look at the big kahuna, which is merge sort, right? We've seen some big O of n squared algorithms, but just to give us a little bit of a preview here, when we come back, we will see something that's more efficient than n squared, which is n log n, that is divide and conquer, which is uh, a different beast entirely in terms of how it works, which is going to be awesome. So thank you guys, and I'll see you all in 5 minutes. All right. So now we come to the sort of heart and essence of this sorting algorithms lesson, which is merge sort. And merge sort is a divide and conquer algorithm. So divide and conquer, as is described here, is a strategy that you'll see with all sorts of algorithms. Binary search that we learned about much earlier is actually a great example of divide and conquer. Divide and conquer algorithms are usually recursive, and they're usually recursive, and they usually have a worst case runtime, something like this. Big O of not n squared, but n times log, or 2, whatever power we would have to raise 2 to get n. And we'll talk about why in a minute. So you can see a lot of different divide and conquer algorithms, and they all share a common approach. You take a problem and you divide it into smaller subproblems that are different instances of the same problem. You figure out how to solve each of those subproblems individually, and then you combine them together, right? So merge sort is divide and conquer algorithm. And let's give merge sort a capital N. Its runtime is big O of n times log n. And it is generally implemented recursively, as are most divide and conquer algorithms. And we're about to see why. So the idea of merge sort is I have a list, and I'm going to cut my list in half, right? I am dividing my list in half. I now cut each half of that list in half. And I cut each half in half again, which with this example of 8 items in my list gets me down to, in the world of recursion, what we call a base case, where I cannot divide anymore. I have to start conquering, so to speak, in terms of the divide and conquer algorithm. And also now, if we take a look at how many levels we have here, and by the way, hopefully this also looks a little bit like a tree, right? I have one level of dividing, Now I have 2 levels of dividing. And now I have 3 levels of dividing. And what's the length n of my list? It's 8. I have 8 items. Remember that log of 8 equals 3. I don't know why I did that. Because 2 raised to the 3rd power equals 8, right? 2 times 2 times, let's see if we can do this. 2 times 2 times TL draw really wants to, I don't know what it's trying to do here, but we'll do it this way. 2 times 2 times 2 equals 8 equals 2 to the 3rd, right? And log or log base 2 of 8 is how many times do I have to raise 2? How many times do I have to multiply 2 by itself to get 8? And it's 3. And so we can see that the number of times I'm dividing is log of the length of our list. And then we combine back up, right? So I've divided, and now my task is to combine. And let me go ahead and grab sort of a pointer here. And let's maybe use the TL draw pointer. And so over here, I need to compare 2 and 8. Well, these guys are in the correct order. So we combine them together, right? Now I need to compare 5 and 4. Well, I realize these guys are not in the correct order. So I need to swap them. I compare 9 and 4, also not in the correct order. They need to be swapped. I compare 1 and 7. Those are in the correct order. Now I need to go through each of these sublists, and it's kind of like I'm going through the whole list. I'm going through my whole list once. I need to compare 2 to 4, because now over here, this guy is the smallest of this bunch. This guy is the smallest of this bunch. This one is the smallest of this bunch. And this one is the smallest of this bunch. Right? So I can compare my 2 smallest. And I know that 2 belongs right there. And now I can compare 8 to the smallest. And 4 is smaller, so it goes there. And I can compare 8 to 5. And I know that 5 goes there. And then finally, 8 goes there. And repeating this operation here, I compare 4 and 1. Well, 1 is the smallest, so it goes there. I compare the smallest here to the next one up over here, which is 7. Well, 4 is less than 7, so that goes there. 9 and 7, and 7 goes there, and 9 goes there. And you can kind of see how we continue this operation. 2 and 1. 1, 2 and 4. 2. 4 and 7. 4. 5 and 7. 5, right? And that should actually be 5 and not 4. Oh no, I think we have 2 4s in here, so that's actually correct. My apologies. 8 and 7. So the 5 is somewhere in I screwed this up a little bit. I apologize. But I think we kind of get the idea, right? And then our 5 goes over there. And really our 4 is going. Oh dear. Our 4 is going over there. And now we compare 8 to 7. 7 goes in there. In fact, we're missing 8 from our answer set here, so let's make a little room for it. And let's throw it into the mix. Right, we compare 8 and 9. 8 is less than 9, so it goes over there. That should be 8. And then finally, we have our last one, 9. Right, so we divide until we can't divide anymore, till we hit our base case. We solve each subproblem and we combine. And so by breaking it into these small steps, it becomes easier to solve. And over here is where we get the log n of the time complexity. And because we had to compare every single item in the list, times the number of levels that we have, I had to do 8 comparisons here. Let's in fact, let's make these guys red. Right, I had to do 8 comparisons, or rather, n comparisons. I had to do it for each level. So I had to do it n times log n times. And that's where our time complexity comes from. So we haven't written a lick of code yet, right? But there's enough going on here where you really want to make a diagram to talk about it. So let me just pause and check in and kind of see what questions folks have before we start writing code. How are we feeling about this idea of, at a conceptual level, what I want merge sort to do? Are we feeling like reasonably good? And how are we feeling at a conceptual level of where this time complexity comes from? Of I have log n, right? How many times I need to multiply by 2 to get my length. I divide that many times, and I have to compare across the whole length of my list for each of those levels. So I get log n from my dividing times n for each of those for my conquering. Cool. So let's leave this up here and let's write some code. I'm not going to lie, this is probably my favorite diagram. It is a little ridiculous, but I do enjoy it. So let's see what this merge sort algorithm looks like. And we are going to have to write a helper function along the way. And so we're going to have merge sort, and it's going to take in a list. And I need to check for my base case where we're already sorted. We can't divide anymore, where if I only have one item, then I'm going to return that array. And this is how you build a recursive algorithm, is you start with that base case, right? But that's for this part over here. We haven't even gotten there yet. I now need to do my dividing. So let's write the code to do the dividing. I need to get a midpoint. So let's get the length of my array and make it an even number. And let's get the left half of my array. And this is where we also make our recursive calls. So we're having the function call itself. And I'm going to use the Python slice to slice from the beginning to my midpoint. And I'm going to grab my right half. And we're going to, again, slice from the midpoint to the end. Right? And so what's happening here is my slicing. Right? Slice, slice, slice. In fact, we slice again here. Right? And so by recursively calling this function inside of itself, we keep slicing. But when I've sliced it so much that there's only one thing in the list, I hit the base case. and we don't keep recursing and calling ourselves, we then just return that number. So I have my base case to stop dividing. I have my recursive call to divide. And now we want to conquer. And the secret here is that as we build this up, we know that each of these sublists is sorted, right? It's kind of silly to say it, but a list of just one thing is by definition sorted. So I can compare these two guys and get a sorted list of just two. And then each of these sublists of just two items is sorted. So once I start conquering, I know that I'm always comparing lists that are already sorted, and that's going to make my life so much easier. So we are going to have to write a helper function here. And this is what we call the merging in merge sort. And we need to return this. And we're merging the left half and the right half. Right? And the job of this merge function that we're about to write is compare 2 to 4 and put 2 here. And then compare 8 to 4 and put 4 here. And then compare 8 to 5 and put 5 here and then put 8 here. Right? So all this pointer logic that we see in other things kind of like builds up here. So let's see what this merge function looks like. And let's go ahead and use consistent names. And I'll just add a nice little comment here. And we'll say merge two sorted sublists. Really merge and sort two sorted sublists, right? Like merge. There we go. I think that's the right way to describe it. We merge by doing a sorted merge so that we get another list that's sorted. So I'm going to need a results array as sort of a placeholder. And I'm going to need some counters. And we're going to need to compare first item, or really compare items in each sublist and pick the smaller. So while my left counter is less than the length of my left half, and my right counter is less than the length of my right half, right? Because what we're going to do is we're going to compare this guy to this guy, this guy to this guy, and then as these get bigger, we're comparing like this. So as I do I along the left side here, when I get to the very last item, I know that I've put everything in there, but I might still have one dude hanging out here at the end, 9. So I need to check both my left and right counters to make sure I grab all the items as I sort. So we have the logic of our while loop, and now we can do our comparing. And we can say if our left one is less than or equal to our right one, and let me fix these names, my apologies. Right, so we're saying left item is smaller and goes next in sorted merge order. And let's name this result just so there's one less letter and it's simpler. And now that squiggly's gone. Right, and once I've done this, once I've compared 2 to 4 and I put 2 in there, well, my counter I needs to go from here to here. So I need to increment my left counter. And if the left item isn't smaller, then we know the right item must be the smaller and goes next. So we say else result dot append right half j, and we increment our right counter because again, I'm comparing maybe over here, I'm comparing 4 and 1. Well, 1 is smaller and it goes here. So my right counter j needs to now get incremented so I can compare 7 to 4. 4 goes there. My left counter I would get incremented. I would compare 9 to 7. 7 is smaller, so it goes there. Here in our while loop, while our j counter is all done, I still has something left. It still has 9 to look at. And so we're just going to add that last one in and we would build up that sublist. And so this merge function and this logic works the exact same, whether we're comparing two lists of one item, two lists of two items, or two lists of four items, and so on. The important thing is that each list is already sorted. And let me make sure I haven't missed anything here because there are a lot of moving parts in this algorithm. But I think we're cooking. And we have merge sort and merge. And if I get a little more screen real estate, we can test it out. Oh, there is actually one step that I forgot, which is the easiest one to forget. Check for any remaining elements if one of the counters has finished. So I did get a bit confused with the logic of this while loop here. We need both I and j to be less than. So if I finishes early and we have something left over, or like we saw over here with 4 and 9, where 1 and 7 both get put in, but there's one left here. I need an extra step to grab anything remaining and put it in. Also, I might have two sorted lists where one has a whole bunch of stuff that just all goes at the end. So we need to append any remaining elements. And we're going to do the same thing for the right half, and we'll call this j. And now we can return some. But now we can, with any luck, test this out. And we can print merge sort, and it looks like our list here is 2, 8, 5. Excuse me, 2, 8, 5, 8, 9, 4, 1, 7. And we'll add a couple print statements in a minute, but let's just run this and see if this works. And lo and behold, we have our list sorted. Let's add a couple print statements though, so we can see what's happening. I think it might be useful to see when we're dividing, right? When we're calling this. So why don't we add a print statement here? And why don't we say, merge sort dividing, and let's pass in the array. And why don't we add some print statements here for merging, and why don't we add here a print statement saying merging, comparing left half, 2, right half. Okay, and that should be, let me put our square bracket in where it belongs. And I think, and why don't we add a print statement here saying merging left half with right half. And we'll just call this pairing. And fingers crossed, our print statements work. This one, you can see how PyAlgoviz, the visualization isn't going to be as useful. So it can be a little tricky. And we see we have a lot of things going on here. But if we kind of look at this, and this is where actually like a debugger can be useful, though I do really think doing this by hand has a lot to be said for it. We can see that we're dividing our whole list here, and we then break it into these two sublists, and we see dividing again. In fact, let's pull this down so we can see the code a bit. Right, so we have the recursive calls that split this list of 8 into 4 and 4. And we see here merge sort dividing. Oh, there we go. The whole thing, our first two recursive calls, 2, 8. And in fact, what happens is the order is because we're recursing, this gets called here. And note that this first left half gets split again. So we go from here to here, and then we go to here. And then it gets split again to here and here. And we see 2 and 8. And then we see merging 2 with 8. Right, so this merge has been called. We've hit over here, and 2 and 8 get compared and combined. And then we hit merge sort, and we're dividing 5 and 8. And it looks like I apologize. I think I got a 4 slipped in here somewhere when this is an 8. So we have here this division and comparing the two, and then the merging. So, right, we called left half merge sort, left half, left, right, merge, right half, left, right, merge. And then we see it here again, and we see all of this left half combined up. And then we see once this first left half recursive call has gone all the way down and combined back up and returned, then we move on to our second recursive call. That's taking the right half and it divides it and also goes all the way down and combines back up. So let me pause here and see what questions folks have, because I realize this is a lot of code and a lot of stuff going on all at once. I'm curious to see what's on people's minds and what might be good to review and go over before we wrap. Okay, and I think the one good thing that might be good to do here actually, I'm not a huge user of the debugger, but this is a great example of when to use it. So let's run debug Python file. Let's try run and debug Python debugger, debug the current active Python file. And it seems to be running. So what you can do with the debugger, and you can do this, by the way, with let's see, Python visual debugger, Python tutor. So Python tutor does the same thing that we're about to do here. And in fact, we can put this into Python tutor and let's start with it there, and then we'll use the debugger. Let's grab our merge sort function and put it into Python tutor. And let's get rid of some of these. Well, I think we have just enough room. I'm going to get rid of some of these comments just so we have a bit more readability here. And let's hit visualize execution. And so now unfortunately, Python tutor now has ads. But when we run this is what a debugger does. It actually is running our code like literally one step at a time. So we see every single step that the computer does. Right. And so here we see we're going to recurse in just a minute. And there we see that recursive merge sort call occurring. Right? Merge sort just called itself and it just got put on the call stack, which is now going down. We see it just recursed again, right? And to go back to our diagram of dividing before conquering, we see the division here happening. We see we're recursing again, but note that we hit our base case, right? The length of the array is 1. And now we see those with that base case, those return statements, and now we're beginning to do the merging. Right? We just tackled the left half of our thing. We broke it all the way down. We have some sublists. And in just a minute, we're going to now merge those left and right halves. Right? And it's just going to keep kind of going down. So there's going to be a lot of steps here because there's a lot of steps here in the merge sort. So I'm going to move through the rest of them a bit quicker. But hopefully this was good to see. We can use the Python debugger to accomplish the exact same thing. If I use Command Shift P on a Mac to open up the debugger, and one of these buttons does it, and I can never remember which. I do have to add what are called breakpoints, which tell the debugger when to stop. So let's put them at our print statements. Let's put one here. Let's put one here. Let's put one here right when we're about to do our midpoint. And let's put one here. And now I think if I run our Python file, there we go. So now I have similar commands in the debugger where I can step into, step out of a function, or keep going, and this will keep going until it hits the next breakpoint. And you can see here the local variables that get created. You can see the call stack, things that get added to the call stack. I could look at each of these different function calls on the call stack to see their different values. So this can be a really nice way to kind of step through your Python code to see what it's doing. I also, to be honest, while merge sort is a little complex for something like bubble sort or insertion sort, actually writing it on a piece of paper and doing this manually, that was what I spent a lot of my CS undergrad doing and a lot of what our teachers had us do. And I think both of these are valuable tools. Some people love the debugger. Some people love print statements. Some people love paper. The important thing is just to have a tool that you can use to help really understand exactly what the computer is doing, like a step at a time, and kind of get under the surface. And then, of course, there's also Python Tutor if you want to tackle it that way, which does have some really nice visualizations. So that is our deep dive into merge sort. We have seen dividing, we have seen conquering, we have seen the better than big O of n squared n log n runtime, and we have seen a recursive divide and conquer algorithm, along with the all-important base case, which any recursive algorithm needs. In the curriculum, it does have a non-recursive, what's called a imperative implementation of merge sort. Note, we also have a very similar diagram here and a couple other diagrams. The non-recursive implementation is a lot more painful. And really the purpose of it being here is so that to see how hard it is to do it this way and to make you appreciate the elegance and simplicity of the recursive approach. And merge sort and binary search are sort of the classic recursive divide and conquer algorithms to begin learning this stuff. All right, so that really concludes our sorting algorithms lecture. Right, we've gone from bubble sort and big O of n squared to the much more sort of beguiling and sophisticated merge sort. I just want to check in and see what questions folks have, what people are curious about, or what might be good to go over. All right, good deal. Gentlemen, thank you very much. Let me go ahead and we'll stop our recording.